All right, so we're going to talk about electric fields now. An electric field is a region around a charge, which another charge, whenever it's placed in that, it's going to experience a force. Now, this idea should be at least somewhat familiar because you're used to seeing it with gravity, or at least you have an idea with this, right? I have a large mass, let's say like the planet Earth, and if I stuck another mass, whether it's a satellite or an asteroid or anything, over here, right, it experiences a force, right? This would be the force of gravity, and it gets pulled in towards the Earth because it's in a gravitational field. So that's the idea with these fields, except now we're going to deal with charges, right? I have electric fields around charges. Now, electric field strength, or the intensity of the electric field, aka the magnitude, the number, not the direction part, that's the force exerted on a small, keyword here, positive test charge, right? Positive test charge. In other words, we determine what's happening with an electric field, specifically the direction, is based upon what would happen to a positive test charge. So a positive charge here, if I put another positive small test charge right here, which way would that positive charge go? Positive, positive repel, so this little small positive test charge would repel away. Thus, the electric field goes away from a positive charge. And if I put a small positive test charge in here, in other words, just a little thing to see what happens, the idea of a test charge, right? Near a negative, my positive test charge, negative, positive, opposite signs attract. So it would come in there. The equation from this electric field is the force divided by the small test charge, or how much force is exerted per unit of test charge there. That's the idea of electric field strength. Now, this equation right here is one of the two equations that you're going to need to bank on, and this is going to be used whenever you have information based upon a small test charge or another charge placed in an electric field that then experiences a force. But we have an equation for force here, and so I'm going to quickly derive this bottom equation for you. E equals, now I'm going to substitute in K Q1 Q2 over R squared, all divided by Q, right? And so one of my Q's here is going to cancel out this Q and Q2, leaving me E equals K, right? So if Q2 was my test charge, K, Q, or the one producing the electric field, right? R squared, which gives me this bottom equation here. Now, this bottom equation is in reference to the large charge. It generally would be considered large because it's larger than the test charge. But this is the charge producing the electric field. So the electric field strength is K, the large charge producing it divided by the distance away you are from the charge squared. So obviously the further out you get away from a charge, the weaker the electric field gets, and the closer in you get, the stronger. In fact, here's a bunch of pictures trying to indicate that. Pictures sometimes can be very good to try to show what's occurring with electric fields. Arrows indicate direction, that's somewhat common sense, and spacing between lines indicates strength. So the closer in we get, the space between the lines becomes much, much smaller than further out, right? So a stronger electric field in here, as indicated by R squared being in the denominator, okay? This is between two positive charges. Remember, positive, positive repel. Likewise, if we put a small test charge over here, it's going to run away from this positive charge, but it doesn't want to come over this way like it would if it was by itself. There's another positive charge over here. My positive test charge runs away. Same thing here, except it's running in, and it can't decide if I put it right here if it wants to go this way or that way, so it'll go to the closest one on in. Notice in the center, right here, perfectly in between them, there is no electric field. The electric field cancels out because electric field is electric field strength, or electric fields are actually a vector as indicated by the arrows. Lastly, I want to point out the electric field strength, or the electric field between two oppositely charged parallel plates. You're going to get a uniform electric field whose electric field lines are parallel, aka uniform, so it doesn't decrease with time, or decrease with distance, excuse me. It actually stays the same all the way through. Now, this is very useful in some cases. For example, in old TVs, tube TVs is what they used to be called, you could put an electron over here at a back plate, cut a little hole in one of the plates over here, and this electron would accelerate through this electric field. Now, electric fields are based upon, the direction is based upon a positive test charge an electron is negative, so it's going to go the opposite direction of the field, right? It's going to accelerate really fast this way, and then you use magnets to direct it. Over here it would hit, let's say, a TV screen, mostly phosphorus, that would light up. And that's the basis of your old school, if you will, tube TVs, is an electron gun using a very strong electric field caused by oppositely charged plates, so you get a nice uniform field that doesn't decrease with distance. All right, I'm going to solve a couple of problems for you. This first one is a plug chug. What is the electric field strength if we are 0.5 meters away from a positive 3.2 microcoulomb charge? So the information that I'm given is all based upon a charge, a large charge if you will, that is producing the electric field, not a small charge in an electric field that's already there and some force is applied to it. So the information I'm given is based upon a large charge there, producing an electric field. Thus I'm going to use this equation. So let me substitute in and plug chug through. And whenever I substitute in my Q here, producing the charge, large Q, K, R, distance to the point that I'm asking the electric field strength. Remember, the electric field strength is stronger in here and weaker further away, right? So substitute the distance away I'm talking about here. I come out with 115,000 approximately newtons per coulomb. I don't believe I talked about the unit for electric field strength. It's newtons per coulomb. Think of the other equation, right? The other equation, E equals F divided by Q, right? The units for force is newtons, the units for a charge, Q, is coulombs. So this unit of newtons per coulomb should make sense to you. I have 2 sig figs in both of these, so taking this number 2 sig figs brings me to 120,000 newtons per coulomb. All right, for this next problem, instead of doing just a straight plug chug through this one, I'm going to use a famous experiment done by Robert Millikan, the oil drop experiment, where he actually showed that the value of an electron is approximately 1.602. He came out a little bit less, 1.59 if I remember correctly, within some decimals afterwards. But he basically showed that charge is quantized and it's based upon the charge of the electron. That's what his experiment proved here. So what happened is he has a big container with 2 parallel charged plates, so there is a consistent electric field, remember, from positive to negative, so the electric field is coming down like this, and it's uniform there throughout. And he sprays in some oil drops, fine mist in, and these oil drops then begin to fall because gravity starts acting on them. He also puts in X-rays, and he uses these to charge the drops. So he gives a different amount of charge to each one. And he's able to actually measure the charge on each one based upon balancing out, adjusting his electric field because of the 2 plates he has hooked up, and balancing out the force of gravity pulling down and the electrical force pushing up. Since this is a negative charge, right, the force on this is going to be going up opposite of that. So let's walk through this problem. Now, in my problem, my scenario, we're actually going to work backwards. He knew Millikan knew what the electric field was, and then he let charges drop through on the oil drops, knowing their mass as well. Then he was able to calculate exactly what their charge was, and he found all those charges were in distinct quanti, or they all had a common denominator of the charge of the electron. But anyway, in mine, we're going to let an oil drop come down with a mass of 2.0 times 10 to the negative 15th kilograms. And we already know its charge. It has a charge of negative 10 E, or there's 10 extra electrons on that. And my question is, what electric field would we need to balance out gravity? So this is a plug chug one here, but I'm going to enhance it with this problem. Talk about this for a second. Really, it's not a big deal. If you're given an electric field and a charge and what force does it experience, so they give you an E, a test charge Q, and ask how much force does it experience, not a big deal. Then you could go to F equals ma from that. In ours, though, we're going to end up needing to solve around 4 force, and you'll see that Y here in a second, but EQ equals F. So now, let's think about what we have going on. We have our oil drop is going to balance out gravity, or the electric field is going to balance out gravity. So gravity is going straight down, right? Force of gravity, pulling the oil drops down, and the electric force is going to be pointing up. Force electric. Reason for that is our electric field is pointing downwards. Notice the negative plate down here, positive plate there. So the electron, negatively charged, goes back up, opposite the field, because the field, remember, is in the direction of a positive test charge, and an electron is negative. So I have the electric force going back up. In other words, the electron's trying to run away from the negative and up to the positive here. And we want to cause this oil drop to stand still. What electrical field do I need to exert between these two plates to cause it to stand still? So sum of my forces must equal MA, and A here, we want it to stand still. A is going to be 0. I'm going to call up positive and down negative, meaning I've got force electric minus the force of gravity equals 0. Now, the force of electric, if we know the electric field, we're going to use this equation over here, and it's a derivative of that equation. One of the main equations you need to know, the two equations with electric fields, this one right here is really the biggest one that you're going to need to know there. So moving that around, solving for F, I'm going to have E Q, or the electric field strength, times the test charge, which is it's not the thing exerting the electric field, right? It's the little charge in the electric field that's getting pushed around, aka here, my oil drop, minus, I know the force of gravity is mg, right? So now I have E Q, aka the electric field that is pushing the Q charge, the oil drop, back up, must be equal to mg. Now we're neglecting some other forces, buoyant force with the air, etc., but that's too complicated for us right now. We're going to stick straight to the basics. Now I know everything here, all of my numbers, except E, so it's plug in numbers and solve through. And once I plug all the numbers through using sig figs, 2 sig figs here, remember we consider how many electrons we have. That is an exact number, infinite number of sig figs. Considering all that, I come out with 12,000 newtons per coulomb over here as the electric field strength that I would need, a very large electric field strength to make these balance out. And like I said, this is a famous experiment. We just worked through the other way, solving for electric field. Robert Millikan actually solved where he knew the electric field strength, so he knew what he charged his plates up to, and didn't know the charge of the oil drops. And based upon what he had to turn his electric field strength up to, he got a bunch of charges for all of them. And as he kept writing down all the charges he was finding from his experiment, what it took to balance out the gravity of the oil drops, he was able to see that they all had a common denominator, all the charges, that is, had a common denominator of 1.6 times 10 to the negative 19th, approximately, charge of the electron.